When the causes of these shut-in wells was analyzed, it was found that only a small minority were factors that could not be addressed. 42% were due to well integrity, 20% due to other issues, 13% to water production, and 8% to sand. With this, operators identified the best candidates and set about chasing barrels. Following that, in 2018, the UK Oil and Gas Authority published their Wells Insight report. This was to document the effect of those strategic initiatives. The report showed an increase of 43.5 million barrels at a cost of approximately 285 million pounds. If we take a look at the restoration activities, we can see a split of the production gain by the category and the unit cost associated. In this case, some of the items have very low unit cost. Notice the relatively low cost, but high return work was in wellhead, valve, and tree repair. This is where visual analytics fits in. So as the saying goes, a picture says 1,000 words. And in our experience, video even more. By viewing the behavior of the downhole phenomena with high definition, high frame rate images, it's possible to understand complex situations with relative ease. And now we can extend this understanding further by quantifying what we see. By analyzing the acquired image and using technology to transform the geometry of the camera lens, it's possible to compute the size, the distance, and area occupied by objects observed within the well. This knowledge is a highly valuable input into decision-making criteria. This is what we're referring to as visual analytics. With the successful launch of our Optus Infinity tool string last year, this has quickly become the device of choice when it comes to visual analytics operations that EV provides worldwide. Through years of dedicated research, development, and engineering, the Optus Infinity was developed to deliver the world's first array side view camera for downhole applications. The features of this Optus Infinity include an array of 4 side view cameras, all aligned azimuthally, providing 100% coverage without any moving parts within the tool string. This enables the creation of a vivid 360-degree map of the well from toe to lubricator. And this can all be provided in a single continuous run-in hole. Combining this sensor with our image processing techniques, we can create a continuous image of the downhole environment through a process we call mosaicing. Through this mosaic technique, the Optus Infinity delivers an image that's 2,880 pixels wide and ultimately infinitely long. The Optus Infinity technologies may be combined with our down view video sensor, providing a forward-looking view, and has the shortest offset between down and side view. This provides the viewer the benefit of a complete perspective of what's happening downhole. And here we can see a closer look of the camera array, including our patented lens design and the twin LED lighting arrays. And this intervention system can be run on all modes of conveyance, be it coil tubing in memory or electric line mode, slick line in memory, electric wireline, and wireline deployed tractor technology. These tools are set up and have been tested successfully and are operating with the ability to tractor while the tools are cameraing. In this example, we see how this technique can be applied to completion components. Here, a mosaic image is made for a sliding sleeve device. If you notice the mosaic process on the far right, it's removing, in quotation, the loose particulates from the final image. These are processed out as they are moving independently from the completion. so they don't appear in the same three-dimensional space from one frame to the next. This is a key feature of the process, as the resulting image quality is often improved through this data processing. The mosaic then can be mapped onto a 3D model of the object created from an engineering drawing or from a CAD model. As before, we can inspect this object from any direction or orientation as we like, comparing the condition of the downhole device with that of the original design file. This information could be vital in understanding the tool performance, identifying component failures, and successfully concluding your root cause analysis. I'll note that all the images, and I'll note that if it appears choppy in your video, that's due to the way we're processing through this webinar. Normally, if you look at my screen, it's quite smooth and very high definition image. But also these images have been generated from side view cameras only. So what you're seeing here is using the side view, then processed, and it gives us the ability to create that pseudo down view image. Here we see the integration of video data with other log data sets. On the left, we see a continuous 360-degree image combined with depth with the multi-finger caliper data. On the right is the 3D visualization of the same data. The 3D shape was defined by the results from the multi-finger caliper. The image was applied to the shape to give an interactive 3D image. You can zoom in and out. You can manipulate it into in 3D views as you like to see the information. The inclusion of the image with the log data helps to understand exactly what's going on and the nature of what's happening in the well. I'll now review a few case stories of using this and our HD Eline camera technology. So the first case comes from a customer who had an issue with a safety valve not closing. Multiple attempts have been made to determine the root cause of the issue, including surface tests, slickline runs, and pressure tests. As no conclusion had been reached, the customer wanted to visually inspect the safety valve as well as acquire ID measurements across the profiles to assist with the planning of remedial work. EV's integrated video and caliper tool string was run to achieve both these objectives in a single run. As you can see in this video, and this is using the side view video of our camera, this video is showing what no other log could, the detail of the damaged spring leading to the failure of the flapper to close. Clearly, we can see the images from the camera. A caliper pass across the safety valve in the same run showed that the assembly IDs were within manufacturer's tolerance of while the side view camera showed some scratches at the lower seal bore. In this case, this allowed the customer to abandon the base plan remediation plan, and they suspended the well until they had a solution lined up. In this case, having a clear understanding of the problem saved the operator valuable time by not pursuing a strategy that was not going to work, and it allowed them to move the rig onto another well and stopped dead time. The cost of this base plan workover was avoided by setting the insert valve. The camera results showed the root cause of the problem, and the operator knew this could not be fixed. The caliper plus camera combo provided evidence of the condition of the assembly. Estimated cost of the base plan workover in this offshore high temperature sour environment was approximately $2 million. The time saved by running the integrated video and caliper in place of providing multiple investigative runs and ultimately perhaps not discovering that the lock spring was damaged was over 36 hours in estimation. The run with the camera was approximately 12 hours. This operator could never have known without the camera, the root cause of that flapper failure. This next example, the operator utilized our HD memory camera. This was to inspect the flow tube and flapper valve condition of a surface-controlled safety valve. Earlier intervention work on the well had resulted in the need to fish tools at the valve, but now the functionality of the valve was in question. There was fluid communication across the valve, but could not access through it. EV's memory camera was deployed on slickline, and here we find the actuated flow tube shifting up and down properly while the camera is stationary. The operator prepped the well by pumping clear water and shutting the well in to allow a gas phase to build at this shallow depth from surface. On the same camera run, but a meter deeper, is a flapper valve, which should open and close as the flow tube cycled. However, you can see the flapper is jammed in a partially open position, allowing fluid to pass by, but not equipment. I'll note that in these types of scenarios, it's very common for EV to add a no-go onto the tool string, allowing us to land and space these optical instruments at known distances to aid in the investigation. There are a handful of methods to remove the flapper. In this case, the operator decided to mill through the flapper with a hydraulic workover unit. The requested EV remain on site to be available to check the milling progress if there were any issues. The flapper was successfully milled, but through a subsequent gauge run, they hung up at 32 meters below the valve. The camera was then deployed to inspect the milled area of the safety valve and the cause of the deeper obstruction. As you saw, the video showed a clean milling job in the flapper area with no hazards to hang up on. However, 32 meters deeper, we find part of the milled flapper has fallen away and is stuck across the wellbore. The operator installed a temporary safety valve and will return to the well later to recover the fish. This case study is a more classic example of how video while tractoring can assist in emergency situations. An operator was attempting to access a subsea production well with a light intervention vessel. The objective was to perform a production logging string on wireline tractor. However, the tractor drift tool string hung up shallow. There was uncertainty over the reasons why, as it was thought unlikely that the isolation valve in the well could be partially open or closed. After multiple attempts to pass the obstruction, the customer requested that EV's video while tractor service used to allow a cautious approach to the obstruction. In this way, the camera was live and logging with surface readout while the tractor was engaged. Downview footage was acquired simultaneous to tractoring and provided the operator with a clear picture of the isolation valve and the fact that it was indeed partially open, despite the belief that that was not the case. As a result, a single run-in hole with the VWT system provided a clear understanding of the problem and avoided the need for multiple potentially risky runs with decreasing drift sizes to see what would pass. The images show the position of the valve and evidence of where previous tool strings had landed off. This provided an answer in a single run. In addition to that, we were able to dimension the amount of opening that the valve was at. So in summary of this case, there were multiple operations run. The multiple drift runs, a lead impression block was run. We then mobilized camera via helicopter and performed the camera operation. After that camera operation, the operator ran in with an electric wireline well key solutions. They successfully opened the valve with the well key solution, passed through it, but then on the way back out, the locking mechanism of the valve must have failed because it partially closed again. So after further attempts to fully open that FS1, it was decided after a second camera run to perform a wireline milling operation. In this case, had a video been on site and run with the first drift run, there would have been a significant reduction of time spent over the whole operation. In this case, 185 hours versus potentially 69 or 70 hours had the job been expected that there'd be a valve ahead of time. Ultimately, the project was a success. Once they recovered access to the well, the production logging was completed and water shutoff occurred. In this case, you can see in the graph, water production was reduced by 1/3 and oil production was increased. This final example comes from a land-based well where the operator acquired a number of older wells with sliding sleeve configuration. The primary objective of this project was to inspect the position of the sleeves, whether they were open or closed. The records of this well indicated the sleeves were not of an open and closed style. Therefore, if a sleeve was determined to be in a closed position, perforating guns were prepared to be on site to be used to communicate with the non-producing zone. An EV provided multi-finger caliper solution was selected with the added benefit to include the new to market Optus Infinity camera in memory mode. By combining the measurement properties of the caliper tool in addition to the visual inspection, EV was able to not only inspect each valve position, but also inspect the integrity of the sleeves and the ports within the wellbore. In this video, the tool string was deployed horizontally via conventional coil tubing, with both the caliper and the Optus Infinity device in memory mode, with data processed once tools were recovered to surface. As we look closely at each of the sliding sleeves via the caliper, the data revealed this particular sleeve position to be an open, however, one of the ports to be partially blocked or damaged. Here we can see the advantages of pairing the Optus Infinity camera with a multi-finger caliper on the same string. The camera clearly shows the situation downhole. Large debris observed above the SSD, and at this moment you can see exactly why the caliper data was indicating the port was partially plugged. The footage shows solids are being produced through that port. In this case, the camera was complementary to the caliper. It completed the picture and provided a full understanding of the situation downhole. And so I'll wrap it up with this slide. The application of visual data analytics has transformed the way we use downhole video. The data density and precision of measurement enable the quantification of features that's not attainable by other techniques. This in turn has led to an expansion of applications for video analysis. I hope that I've demonstrated how the use of our technology can assist in your valve remediation efforts. I appreciate your time, and we'll pass it to Mike to go over if we have any questions to address.
Yeah, we'll open it up to any questions. Please fire them away in the chat channel, or you can use your mic directly. Just jump in, folks.
Mike, you there?
Yep, go ahead.
Yeah, this is John Friedley with Tucker Energy Services. How do you deal with like stick slip problems with tools kind of rushing past, you know, sticking and then flying uphole? You know, kind of that uneven speed where you'll end up stopping and then build some tension, and then the tool kind of flies by.
Yeah. Excellent question, John. And nice to hear from a Tucker alumni. I spent time there myself many years ago.
Okay.
Cut my teeth in Canada at Tucker 20 years ago. Yeah, so to answer that, it has to do with the resolution of the video. So we're recording at high frame rates, and with that, any stick and slip, we're actually able to better capture that video, and then of course we can pause it using data processing later. Maybe I'll let Jordan or Steve, can you add to that?
Yeah, I mean, the frame rate typically is 30 frames a second on our memory and then our new read line as well. So that definitely allows you a little more leeway in that regard. And I've seen running whole, even when we're not trying to actually log certain things, trying to get past it, just go through some tubulars, you can still make out some detail in tubing going like 120, 150 foot a minute at times. Just depends on the size of the pipe. But yeah, so the resolution and the frame rate definitely helps you out in those regards.
It's kind of an extension of that. I mean, is there any way to sort of back that into the real depth, or are you able to kind of mathematically correct your depth file to get you? I mean, obviously you can see piece by piece what you're looking at, but I wonder if you're able to sort of fold that information back into the depth file.
Yeah, that's a very valid question. And we've had a number of operators approach us with projects similar to what you're asking for. We believe the use of this high frame rate video, and specifically use of our Optus Infinity product, will be able to help in future all logging tools with more accurate depth control, and exactly that, to address your stick and slip situations. It's not necessarily ready today, but it's something that we're working on, and could certainly talk to you offline if you have specific application.
That's very interesting. That's good news. Yeah, nothing particular at the moment, but it does come up sometimes.
Okay, thank you.
So we got a few questions in the chat channel. Some have been answered, but we got a good question from Erosion. He's asking about fluid clarity and if there's any special fluid medium to run this tool in. Do you want to go on to explain a little bit about nominal turbidity units and what we can see downhole?
Yeah, sure. Good question. I have a slide for this. Okay, so the fluid clarity in the well, obviously we're operating with an optical instrument. There's two factors as far as what can affect our ability to see in the well. One is the amount of turbidity or particulates floating in the well. The other has to do with the pigment of the fluid itself. And so ideally, and the kind of easiest method to check the fluid clarity is to drop a coin in a glass. And if we can see the coin, as you can see in this case, if we can see the coin, then obviously the optical instruments will work fine. What we're seeing here is not just turbidity, but the pigment. So the water and the cola have very, I don't know what's happening with my computer. The water and the cola have similar turbidity, but the pigment of the cola is dark and can cause problems. See if this makes it easier. No. I don't know if I answered the question or not, as I'm a little distracted by my computer not behaving the way I'm expecting it to. Was there anything else, Mike?
Yeah, I've got a question here from Charlie. He's just following on from Erom's question regarding fluid clarity. Could this technology be deployed alongside a jetting tool in order to displace any debris?
Alongside a jetting tool?
Yes.
That's a complicated question. So we do have solutions with specific operators where we are able to provide downhole video at the same time as being that solutions. We can certainly take that offline and talk to you closer, but that's a product that we have in combination with another operator. Another method is deploying this tool on coil tubing. We do have a shroud system where we're able to pump fluid over the camera and spot a clear fluid. So jetting is one thing, and when I hear jetting, I'm thinking of you want to actually stir up and clean the well versus just to clean the fluid itself and spot a clear fluid for the camera. So we do have solutions for both.
Okay, we've got a question here from the vendor. He's saying that this camera is recording subsurface, pull out of hole, and then we see the pictures or video. In any system, we can see downhole real time. So the answer is yes. Jeremy, do you want to go on about our real time cameras?
Yeah, you bet. So some of the examples that I provided were in memory, others were live. And so with the Optus Infinity, we can provide, the tool is actually in hybrid. So we both can provide live surface readout of that video, as well as storing the data within the tool. And this enables you to use whatever platform you happen to have on site. So if you only have conventional coil or slickline, we can set the tool into memory mode and operate that way. Where if you have the ability for electric line service or a fiber optic, then we can then stream that data back up to surface and from the well site to anywhere.
Okay, we've got a question from Lawrence. Does the camera have a means of having increased light to enhance visibility?
Yeah, we have the ability to adjust the light in the real-time mode while in hole. So that's one of the added advantages of our specialists being on site. Our platform is primarily provide a service. So one of our engineers or field specialists will be out with these tools. They provide the on-site expertise as far as well clean out, what we should expect, and then while in hole, they have the ability to adjust the lighting and the resolution in order to pick up the definitions and what we're seeing in the hole.
Okay, any other questions, anyone? Feel free to fire them in the chat channel, or you can use your mic directly, whichever you prefer.
Good morning. I have one question. Is there the ability to control the zooming of the camera and the focus and all this based on the situation that will encounter the downhole? I mean, like a control in and out for the camera during running downhole for the zooming and all this.
Fraser,
yeah,
would you be available to answer that?
sure, no problem. I saw your question, Rashid. I was going to text back. So yeah, the camera, we have full control of the camera from surface, and that means we have full control. We can adjust the light settings, we can adjust the focus or the shutter speed, the gain, and the resolution as well of the camera. We can rotate the camera with a motorized motor and rotate the side view camera. So yeah, so we've got full control. So whatever we see downhole that requires any adjustment to the camera, be it light or we need to rotate it, then of course we have full control at surface. Hope that answers your question, Rashid.
My question. Second one that I have is in the case of some reason there is some like stuck or lost in hole, what is the risk of this? And is there any method, special method for fishing? It will be like other line.
Yeah, that's a fair comment. The tool string is a logging string. It doesn't have any external apart from centralizers that are added to the tool string based on the well that we're running. But your fishing techniques will be similar to that of any case tool logging service. And imagine a bond tool. Picking a tool up would be similar to that.
Okay, thank you.
I have a question.
Sure.
Yep, go ahead.
Yeah, just when you run with the camera and you need to run just to compare or to confirm with the Caliper thing. So this is, it will be in separate runs, so you cannot combine.
No, we can combine. So we can
Okay, in case of combination, how it will be the deployment?
I'm sorry, I missed the last word.
How to combine? How the camera will be combined? Which one will be?
So the camera and the caliper, we have a post-processing service through our Epidote product line, where we can take the caliper data, whether it's run at the same run, or if it's a previous caliper, or run independently, and combine that with our video data. So the output will provide you with a caliper, and while you're looking at the caliper, you're able to select video or images in the same presentation.
Okay, thanks.
I guess there's some spacing between the caliper and the camera. I mean the distance. What is the typical distance? What is the typical distance between the camera and the last position of the caliper log?
Fraser, are you able to help me with this one? The distance, what I heard was the distance from, say, the side view camera to the caliper, the business end of the caliper tool.
Yeah.
So basically, we have to talk through a configuration. If you're running a down view camera, a side view camera, and a caliper, or integrated video caliper string, we call it. The down view camera is at the bottom, and then half a foot above, you have the or 18 inches. Sorry, that's not half a foot. 18 inches above that is the side view camera, and then from the side view camera to the bottom of the fingertips of the caliper is approximately, depending on what centralization you're going to have, you're talking around about maybe 4 feet, 4.5 feet from the side view camera to the lower, the bottom of the fingers on the caliper. So we can obviously run, if you're asking to run a caliper, but you want to run the camera as well, you want to get there is a configuration that we can run, and that can be with the camera. We can remove the side view camera, remove the motor, and then we have the camera, which is only going to be about 2 feet from the end of the fingers to the camera. Or if you want to run it independently, we can put a bull nose at the end of the caliper, and then you will have much closer to the bottom, basically, the caliper.
So it can.
Thank you.
So it can be combined with all the downhole monitoring tools, or just there are some specific tools that can be run with, like what you mentioned, Caliper.
So if you're speaking about running the camera with logging tools, there are a handful of devices, and honestly, they're specific to the situation and the operators that we're working with. So generically speaking, calipers, pressure, temperature, CCL are fairly readily off the shelf for us. Anything further than that would require a discussion with your local sales team on what we can offer. However, the post-processing, we do have the ability to take that data if it's not in a combined run and put that together through the use of our PIP product with Epidote.
Okay, thank you. Thank you very much.
Okay, we've got a question here from Lawrence. Can all cameras be run on both slickline and E-line? In the past, we've been told of the limitation of having a real-time camera being run on slickline. Does that limitation still exist?
Okay, yeah. So the answer is yes and no. It depends on the technology that we have in the location that you're at. The new Optus Infinity hybrid tool is now able to the operator can choose and set up that tool in memory or live mode. Our alternative technologies are a dedicated E-line downhole tool and a dedicated memory downhole tool. So in some aspects, you're right. If we have deployed an E-line system and now require it to be in memory, there may be some added tools that need to arrive to go with that kit in order to turn it into a memory-only tool. Assuming that's not our hybrid Infinity, which comes complete to run both. Fraser, if you can add to that, I think I described that well.
I think you described it, Jeremy. Yeah. So there's various types of cameras, like Jeremy just mentioned. But yeah, of course, we have a set of tools that runs specifically on memory, and we have a set of tools that are specifically surface readout. Or as Jeremy says, we have the hybrid Infinity tools, which effectively can be run on both, depending on customer choice. There's an option out there.
I'll just add, I'm now on our website, and so if you're looking for further information or someone to our website, ecam.com, you'll find all sorts of different examples and case stories of the type of work we do,
Jeremy,
including the. Yes, sir.
I think you're still showing the slides. We're not seeing the website.
Okay.
Thanks.
Thank you.
I just got last question is when you do this comparison between, for example, the caliper and the camera, the caliper it's giving for us, let's say, some quantitative data, where the camera is giving some, let's say, informative data or estimation. For example, there is no risk, for example, that the caliper saws some things and you cannot see with the camera and can lead you to some misinterpretation if you want to combine both of them or the inverse.
Rashid, I can take that. Yeah, so basically what you're saying is absolutely correct. The camera is there as a qualitative measurement tool to actually visually understand and visually identify. The caliper is quantitative. Quantitative. It will actually give you the measurements of the idea of the tubing. However, what the caliper does is it's got a very limited or a very radial coverage, where the camera gives you this 360-degree radial coverage and the view of things that could be sometimes missed, such as pitting and erosion, not picked up the caliper, but it's identified with the camera. I think Jeremy did show some examples of what the camera can do in terms of actually dimensioning analysis, where we can now measure with the camera. I think he showed it on his slides, yeah, with the side measuring some pictures in the casing. That particular well that I'm showing you, we actually ran the camera in that well after a 60-arm caliper had been run in it. And the caliper came out of that hole showing that there was no signs or very minimal signs of erosion, corrosion, and pitting. When we actually ran the camera, that was a different story. So going forward, and just to give you an indication of what's going on in that particular well, we now do time lapse in that well of this exposed section of 10-inch casing, and we do a time lapse. Go back in with the camera. There's a caliper run as well, and we visually inspect if there's any further development of the erosion. So the camera really is there to complement the caliper, but the caliper is there to give you your exact readings of the IP. Hope that answered.
Yes, thank you.